Hey everyone, people hear me fine at the back? Cool. My name is Diptanu, and I work at Facebook in Menlo Park, California. So this talk is going to be about cluster schedulers, and I'm going to try to dissect a cluster scheduler and talk about the things that make a cluster scheduler, and really the first principles behind a cluster scheduler, right? How many people here have worked with something like Kubernetes or Mesos or Nomad? Quite a few hands, or even Docker Swarm. Okay, cool. So schedulers have been pretty much like all on rage for the last few years. I've been working on schedulers for quite some time now, I think for the last 4 or 5 years. I used to work at Netflix, where I wrote the open source scheduler called Titan, which is, I think, open sourced last week in the name of Titus. So yeah, I was the lead developer of that project. And after that, I went to a startup in San Francisco called HashiCorp, where I was the lead developer of an open source scheduler called Nomad. My background is mostly in developing schedulers and so on. So in this talk, I'm not going to be talking about a specific scheduler or a particular scheduler. I'm going to be talking about schedulers in general, like how do you evaluate a scheduler? How do you know, like, why do you use a scheduler, and B, like, if you use a scheduler, is your scheduler good enough for you, right? Or if your scheduler is not good enough, what are the parameters in which, like, you weigh in, or like you understand whether your scheduler, how well your scheduler is designed for your infrastructure? This talk is based on a recent paper that I co-authored for ACMQ. So if you are, if you want to like read more about it, this paper is a good source. And most of the material of this talk is from this particular paper. Someone once told me, like, when I was beginning my career, is that developers and the act of writing software is just maybe like 25 to 30% of like the entire software development lifecycle. Once you write a piece of software, or once you write a service, then like the battle is about deploying the software and keeping the software running, right? Like deploying a software is step 2, right? After step 1, writing it. Step 3 is like keeping it running. Like what can you do to make sure your software doesn't go down during the Super Bowl or something like that, if you're in that kind of a business, right? So a lot of like the deployment pipeline is around how do you deploy a software and how do you keep it running. And I think my personal opinion is that the last 10 years, there was like a rise of like the whole so-called DevOps movement. Basically, in the DevOps movement, deployment automation was like at the heart, right? Whenever people talked about doing DevOps, it was always about, okay, how do I take my system to production? And when it is in production, how do I keep rolling new updates and so on, right? If you look at Etsy's blog, like you'll see like them doing like 1,000 deploys in a day. Or at Netflix, we did even more than that. Thousands of deploys in an hour or so on, right? So a lot of automation and DevOps is about actually like pushing software into production. In general, in the last decade or so, service automation was basically like left to supervisors, right? You would have systemd or RUnit or any of those PID1 supervisors which keep a software running. You would use Chef or Ansible or something like that, and let the PID1 of like of a node keep your software running. And if your software crashes, like systemd or something like that, would restart your application, right? So a lot of this was left to like supervisors, right? There was no like a holistic view of like how the software was running in a cluster. And as a result of that, there was a very static view of the entire cluster, right? What it means is that you looked at your cluster and you said that this 10 machines are going to be running this service, this 10 other machines is going to be running that service, right? So there was a lot of like of doing like accounting of resources based on a very static view, right? Once you deploy, your understanding was that the cluster topology would not change unless there is a machine level failure, right? And so, like, scaling up and down or like reacting to users was harder in those kind of situations where you have to scale out horizontally based on like traffic and so on. So what I think like happened as and when like we went from running services, from tens of hundreds of machines to like a data center, like running like your service in like tens of thousands of machines on the cloud, is that we thought that there was a need for service management tools to understand the cluster topology, right? So if you're on Amazon and if you have to like scale out based on your traffic or your some other metric, you use something like an autoscaler, right? An autoscaler is nothing but a scheduler which understands cluster topology, right? It shrinks or grows your cluster as and when like the metrics tell you to do so. So we started connecting service management with how cluster topology needs to look like. And from there, we came into the whole space of doing dynamic cluster schedulers. Right, 3-4 years back, I think that trend started when Mesos was open sourced by Twitter. I think that was the very beginning of people having access to cluster schedulers. But having said that, cluster schedulers are not new, right? Google had Borg running for since I think like early 2005 or 2004 and so on. Even if there was no dynamic scheduler, people were doing some sort of scheduling by saying that, okay, I want to run my service in this X number of nodes. So what does a service scheduler give, right? A service scheduler gives an like self-healing capability. What it means is that if your node dies or if a service dies, the service scheduler will bring it back up, right? That is the guarantee that you are getting. So if there is a hard disk failure or like a network failure, if your service scheduler sees that a service or a shard of a service is not running anymore, it would basically start it somewhere else. And not only that, service schedulers provide an API for data center operators to run your application, right? So if imagine fork exec, right? You're using fork exec on a POSIX compliant operating system to start a process, right? A service scheduler or a dynamic cluster scheduler is like fork exec, but for your data center. It gives you an API to run your services in your data center computers, right? And I think the other important aspect is it provides the quality of service guarantees. Now, what do I mean by quality of service guarantees? It means that if your service wants like 4 GB of RAM and like X amount of hard disk and X amount of network resources, your service scheduler is going to give you the guarantee that it's going to get that many compute resources on any node where it is running. And if the node dies or if there is some other hardware failure, the cluster scheduler is going to move you that workload on a machine which can provide that guarantee. So if you have wanted, say for example, SSD drives on top of which your service wants to run, if there is like some disk failure or other node failures, your cluster scheduler is going to move that service from a node which has SSD to another one which has similar hardware, right? So I think that's very important. So what does a cluster scheduler look like? I think like a cluster scheduler looks like this. You have your deployment systems like Cloud Foundry or other systems like Spinnaker or any other deployment tools like Terraform, or like even things like MapReduce or TensorFlow, which are basically like application level systems, right? Whose concern is to like deploy new services or deploy new processes. Then like they talk to a cluster scheduler, right? And the cluster scheduler understands that, okay, like I need to run this many tasks or this many shards of a service, and then it talks to like the clusters, and then on the clusters where the compute resources are present, it runs those services, right? Now, how many clusters are being supervised by a cluster scheduler is left to the scheduler based on like the scale and capacity guarantees that the scheduler needs to provide. And a scheduler essentially looks like this. It has three main components. It has an allocation management, which basically provides an API to services like Terraform or Cloud Foundry or any other PaaS, and basically receives allocation requests, like these are like the jobs that I want to run, or these are the tasks that I want to run. And then it talks to an actual allocator, right? The allocator has things like constraint matchers, right, which understands the constraints that the user wants to impose on a job. And then it finally talks to a resource manager, right? And I think based on like whatever systems you look at, like for example, if you look at any scheduler, right, like Mesos-based Marathon or Aurora, or if you look at Kubernetes, or if you look at Nomad, essentially, like you'll find these components, right? For example, in Apache Mesos, right, Aurora or something like that, the frameworks are the ones which does allocation management, right? And also, like they do allocators, right, which the frameworks basically decides where to run a task and so on. And then finally, like they have a resource manager. In the case of Aurora or Marathon, it's the Mesos master, which knows like what are the resources present in the cluster. So that's pretty much, I think, like the building blocks of a cluster scheduler, right? And in the allocation management, things look like this, right? Basically, they all contain a finite state machine, and the finite state machine contains the state of a currently running allocation, right? What I mean by the state of an allocation is basically like when you submit an allocation or when you submit a job, the job is pending because right now like you are not running anything, so obviously like the state of the job is pending, and then once the scheduler finds a node where the job can be run, it goes into running and so on, and when the job completes, or if, for example, the job you don't need to no longer run the job, it goes into like the dead state, right? So every scheduler has a state machine like that, like it maintains an internal state machine. And the purpose of the state machine for the allocator is to see what is the desired state and what is the current state, right? So if the current state is that there is 5 shards of your service running, but if the desired state is 10, that means the allocation manager is going to create like 5 more shards so that it can match the desired state to like the current state. So pretty much that. If you want to get deeper into this, the Borg paper, which was published by Google a few years back in Eurosys, is a good reference. And the state machine, diagram of the state machine is essentially from that paper. The allocator is, again, okay, the next level, the next layer of the cluster scheduler. The allocator basically provides an API to the allocation management systems to create new allocation. What it does, it basically has a constraint matcher. Now, what is a constraint matcher, right? Let's say like you have to run a job on machines which have SSDs, and or like you want to run machines which has 10 gigs of RAM, right? Now, let's say not all the machines in your cluster or in your data center have SSDs or have 10 gigs of RAM, right? So the constraint matchers is going to filter the nodes where a particular job can be run, right? So it's basically like filtering from a list of nodes to like a smaller subset, which are ideal for running like your job, right? And then it also provides a facility for ranking nodes, right? Let's say like you have 2 SSD nodes or like 2 machines with 10 gigs of RAM, and one of them is least loaded and compared to the other, and you want to increase resource utilization, right? So in that case, putting a job on a machine which is already highly loaded is better because then you get better utilization. And that process of determining which machine is best suited for running a shard of your application is the basically like what the ranking facility does, right? So that's an allocator. So what a scheduler looks like is you provide a job, and then like you are filtering through like a list of nodes based on constraints, and then then you apply things like a bin packer, which basically ranks nodes and ranks nodes based on like the utilization and other things like priorities, and then finally creates the allocation. So this is pretty much like how like a scheduler would look like, a cluster scheduler would look like. And the final piece is the resource manager. The resource manager tracks all the compute resources in a cluster, And it also tracks all the nodes which are currently healthy. For example, like all the nodes which are, for example, like network partition, the resource manager would know about that. And it would know that, okay, like this node is not in the cluster anymore because of some failures. I need to inform the allocation system about that so that the allocation system can now place the shards or the tasks which were running on that failed machine into another healthy machine. And one critical thing to notice about the resource manager is they're always strongly consistent, right? So, for example, in the case of Mesos, they use a variation of Paxos to maintain like the state of the cluster. In Kubernetes, they use etcd for maintaining the state of the cluster, and in Nomad, we implemented Raft, which maintains the state of the cluster. The reason why they are strongly consistent is because you don't want to not know what is the current state of a scheduler, so that if you have 2 or 3 schedulers running in parallel, they can make the right decision based on the actual state, so that 2 schedulers are not making conflicting decisions. Actually, like there is probably like a subtlety to that. In cluster schedulers, it's perfectly fine to make conflicting decisions, but then you have to know that there were some conflicts, and then you have to resolve the conflicts and so on. That's probably like a more in-depth conversation, so I don't want to go into that. But something to remember is that most resource managers have a strongly consistent view. And on the compute node, things look like this. You have the scheduler agent, and then you have things like a volume manager, you have a network manager, and then you have a QoS manager. Usually tools like Docker provides those facilities which run on top of an operating system, and then like the scheduler agent uses those facilities to run the tasks, like which are basically like your process or your application. Something to remember here is that based on which operating system you are on, like you would probably do things differently. Based on what kind of volume management you would do things differently. For example, in Apache Mesos, there is a facility called executor, which basically runs the processes, which supervises the processes and so on. And it uses something like C groups in Linux. C groups is the facility which provides the QoS guarantees. So like if you have asked for X amount of RAM and X amount of IOPS from the file system, like the QoS is being offered by the operating system using the C groups API and so on. So basically things look like this. Based on which operating system you're running and what you are doing, like things would vary a little bit. But overall, pretty much like all the schedulers do the same thing. If you're on Kubernetes, you have the kubelet, which is the scheduler agent, and the kubelet uses cryo, which basically talks to Docker or runc or something like that, and then creates the containers, and then that launches your tasks and so on. So pretty much like all the schedulers that are open source today like work in a similar manner. And from here on, I would talk about something that every scheduler operator needs to remember is that considering the failures that can happen when you are running in a cluster scheduler is, to me, by far the most important things. That's because like we were using cluster scheduler at the first place to mitigate failures and to make sure like we get good quality of services from the underlying operating system. So planning for failures when you're designing a new cluster scheduler or evaluating a cluster scheduler is super important. So let's talk about node-level failures, right? It's very important to do capacity planning. I don't see many people take capacity planning very seriously these days, especially on the cloud. And even if they do capacity planning at an aggregate level, right? They talk about, I need 300 instances to run like my service, or I need X amount of instances to run my service. But things don't look like that anymore today, especially with things like service mesh and so on. like you are running other software which are helping all the containers which are running on a node. So when you are using things like sidecars and so on, you need to account for the resources that your sidecars are going to take, right? What happens when when Envoy or like any other sidecar you are using uses more RAM or uses more resources that you didn't account for, right? Or like what happens if you're using ZFS on Linux, what happens when your ZFS is not tuned properly and the ARC cache of the file system is taking half of the RAM. And by the way, like I was in an outage where we were using ZFS back in the day at Netflix for Titan. And little did I know about ARC cache on ZFS, and I didn't tune ZFS properly. One day, like I get a page from like some machine learning team saying that, hey, like how come like half of the node's memory is like gone? And I found out that it's basically ZFS has taken half of all the available RAM on that machine. And very recently, like I was in an outage where we had, because someone wrote a log rotate policy based on number of days. Say for example, like you write a log retention policy for say 5 days, but you have a finite amount of disk. If an application misbehaves and like it starts producing more logs that you can't hold for 5 days, you're obviously going to get an outage because your disk is going to be full. So capacity planning at the node level is super important. You have to know like what resources the applications that are running on the node are consuming. And second is killer. Now killer on Linux today is basically a mess, right? The way killer works is not very deterministic. So if you have like 5 or 6 applications running on the same node, or like if you have like 10 containers running on the same machine, and for some reason one of them are taking a lot of memory, the killer is not smart enough, at least today in Linux, to know like which container is violating like the resource usage limits, and it can basically shoot any of the containers down. So even though like you have an application misbehaving and using a lot more RAM, like someone else could be penalized because of that, right? So one strategy that I have used in the past is, instead of letting the kernel do killing, make the decisions of killing containers in the user space, right? Because you have scheduler agents which know like the resource usage of like containers. So instead of delegating that responsibility to the operating system, take that upwards and disable the kernel's killing capability and just kill containers, or make sure containers go away when they're violating the quality of service guarantees that they had asked for. That way, like things are more deterministic, and when there is an outage, like you can reason about things in a better way. Leaking container resources. Even though like Docker is super popular and it's been around for like quite a few years, or things like Runc has been around for quite some time, the momentum of those projects are super high. And as software developers, we introduce bugs, right? Like it's natural, right? Software is going to have bugs. So even though pushing out new versions of tools like Docker is super important because of things like security fixes and so on, I would say that like rolling out system software after testing for a long time is super crucial, so that like you understand like if there are regressions in those software, and understanding what those regressions are, so that you can again reason about them when there is an outage. We optimize for node level efficiency, but there is something to say about cluster level efficiency as well. So things like EBS, for example, right? Things like SAN, right? Like network storage device and so on. So for example, like all your nodes are using a SAN, and like you have like hundreds of machines in a rack, but there are limitations at the rack level, right? You have a top of rack switch or something like that, which can only like push that many bytes, right? So over provisioning at the node level, or caring about efficiency at the node level, is fine, but you have to also think about what is happening at the rack level. What is happening at the cluster level? Am I oversubscribing resources at the rack level? So even if you have asked for like 100 IOPS or at a node, you won't get 100 IOPS at a node because your top of rack switch is not able to like push that many that many packets from all the nodes in a given rack. Multi-tenancy, again, in Linux is kind of a mess. One of the promises that brought people into using containers in the first place was that, oh, we can make resource utilization better. But what it means when you're increasing resource utilization is that you're running in a multi-tenant world, right? Like you're running like more than one container on a machine. But because like the C group story on Linux is still not great, like there is a lot of multi-tenancy problems, especially with over-provisioning of like RAM and CPU and so on. And the other thing is like vector instructions. Like vector instructions are getting more and more prominent. Like for example, AVX 512 instructions or any other SIMD instructions. Say for example, you have a container running vector instructions and another container not running vector instructions, right? So what would happen is, because vector instructions take a lot of power, the processor is going to scale down the base frequency. So now, even though like your processor's base frequency is say 3 gigahertz, just because one container is running SIMD instructions, you won't get that much like base frequency. And the application developers would be confused in terms of like the cycles that they're getting from the server. So I would suggest like using node pools for co-locating workloads, which are similar in nature. So if you have machine learning workload, which are using SIMD instructions, put them in a separate cluster, then say like lower latency services, which might not be doing SIMD instructions and so on. So on the cluster level failures, I would say the most prominent failure that I have seen happens from software pushes, right? So when you are pushing software that many times, no matter what you do, like you're going to have some bugs, right? And so rolling deploys are like a must, and you need to have like a good feedback control loop from your deployment system into your scheduler so that the scheduler doesn't get rolled out. And like, you can stop deployment of your new scheduler agent or something like that when there are problems. System software problem failure, again, like if you're running Docker or something like that, make sure like you don't deploy Docker on the entire fleet, like a new version of Docker in the whole fleet. Roll out those kind of changes in like, say 10% of the fleet or even less, like I would say 1% of the fleet, and see how things are behaving, and when things behave properly, then roll it out incrementally. And it's okay if it takes like a week to push out the next version of like a system software, but you would get like better stability from doing such things. Global resources. For example, if you have like a global resource like ENIs on Amazon, elastic network interfaces, or say for example, the number of IOPS that you can do on your block storage device like Gluster or something like that, making sure you consider that there is a finite amount of such things, right? One of the things that happens is when traffic goes up, you might want to auto-scale the containers that you're running, but put a ceiling on top of like how many containers or how many nodes you're bringing up, because that would like save or like make sure like the global resources that are that you depend on are not getting saturated. And budget for things like how much failure you can tolerate. Especially with things like network IOPS. Control plane failures, as a scheduler developer, I think are most interesting to me. Again, as I said, most resource managers have a consistent view of data store of the cluster. What it means is like they use things like Paxos or Zookeeper or etcd. Now, what happens with strongly consistent systems is that when there is a network partition, you can't read or write from those data stores, right? So if you have a scheduler depending on something like Zookeeper, and whenever you have to make a new allocation and you need to write to Zookeeper if there is a network partition, now you can't put new allocations, right? So, and things like that is going to happen, right? If you're running something like that, be prepared for that system to go down. Be prepared to lose the entire node, like the entire cluster of your data store, right? So what is important is during that time, like your cluster scheduler should not start killing your containers or your services, because now then you have two problems. On one hand, you can't do new allocations because your scheduler is not able to do that. And on the other side, the services which are already running are going to go down, right? And if you're making money from something from your website which shows movies to people, you are losing money, right? Um, and reconciliation is very important. What I mean by that is, like, say, for example, if a shard of an application goes down, your scheduler is going to try to reconcile that by bringing up another shard. And there are usually like two different ways of writing cluster schedulers, right? One is edge-triggered, and the other is level-triggered, right? Level-triggered schedulers are super dumb, right? They're usually like a loop, right? They're running like every 300 milliseconds or something, and they're comparing the desired state and the goal state, and they're reconciling. Most schedulers, Mesos schedulers, and even the scheduler in Kubernetes, the one which comes out of the box, is level-triggered. So they're simpler and they're easier to reason about, and they get like a fair, good amount of consistency. On the other side, edge-triggered schedulers, which is what we did with Nomad, they're event-driven, right? So whenever like there is a new event in the cluster, Nomad is going to make a new decision and it's going to put a new allocation. Now, what happens when you lose an event, right? When you lose an event, your cluster is not going to make any progress. So while those edge-triggered schedulers are super fast because they're event-driven, like for example, in Nomad, we can schedule like 1 million containers under less than 5 minutes or something. Like that was like 2 years back. I think it's even better now. I don't know the results of the new benchmarks, but even this another scheduler from Berkeley, Apache Sparrow, it's also an event-driven scheduler, and it also gets like sub-millisecond scheduling performance. But again, they're hard because you can lose an event, and what do you do when you lose an event? You have to think about those kind of edge cases. Implementing quotas. Wherever you're running Google Cloud or Amazon or your own on-prem hardware, there are going to be days when you're going to lose a data center. There are going to be days when you lose a cluster or a rack. So it's very important to implement quotas, right, in your scheduler. Because when you implement quotas, what you can do is you can say that the front-end jobs or like the end-user jobs, right, for example, the website or something like that, are the super important jobs, right? If they go down, we can't run our business. But things like machine learning jobs or batch jobs, which can run at some stage later, like, are not so important. So you assign lower quotas to them so that on bad days, when there is an AZ outage, when there is a region outage, your scheduler is going to prioritize the most important business-critical jobs so that like you can still run your businesses. Plan for scheduler outages and be prepared to like even reboot your data center. For example, in one of the schedulers that I wrote, like when I was at Netflix, we did that calculation. It took us, if we lost the whole region, right? Say, for example, if we lost US East 1, like it would take you like 45 minutes to bring up all the containers which were running before the data center or the region went down. So those kind of calculations, those kind of capacity guarantees are super important to know beforehand. Like, what if you lose a whole data center? Like, how long does it take for you to get the whole data center back up when you lose a scheduler and so on? That's pretty much it. This talk is pretty much based on this couple of papers. If you're around and want to talk more about schedulers, I'm here, or hit me up on social media. And thank you.